Hello guys, welcome to my channel, and in this video I'll explain to you article number 2.5, potential due to a system of charges. So we have a number of charges, their system of charges, and we'll find a potential due to all these charges at a point. Okay, so let's start the video. Consider a system of charges q1 q2 up to qn with position vector r1 r2 rn related to some origin. So there is a origin and we have to some origin. The position vector of these points are like this. Okay, r1 r2 r3, this all charges have a position vector r1 r2 r3 respectively. Okay, and now we have to find the potential due to these charges at a point p, which are distance from q1 charge distance is r1p, from this is r1 r5p. Okay, so this is the distance of the all the charges from this point. We have to find the potential due to all these charges. Okay, now so potential due to one first charge will be what? Point charge. We know the potential value, we have studied. Okay, you can check the previous video, then you can understand how we arrived at this. Okay, similarly the potential due to second charge will be this, third charge will be this. Okay, nothing new in this. Okay, the distance is there, it is a scalar quantity, where r2p and r3 are the distance of p from charges q and q3. Okay, you can see from the diagram, and so on for the potential due to other charges. By the superposition principle, the potential v at p due to the total charge is the algebraic sum of the potential due to individual charges. We apply the superposition principle, and what's that the total potential at this point will be the algebraic sum of the all the points. There is no vector because it is not a vector, so we'll just add them. Okay, scalar sum, algebraic sum will do. So the potential will be just the sum of the all the potential. And now taking the sum, this is what we got from the equation. If you solve them, 1 upon 4 pi epsilon naught get common, and in the bracket this will be q1 by r1p plus q2 upon r2p. Okay, now if we have a continuous charge distribution characteristic by a charge density rho r, we divide it as before into small volume elements, each of size del v and carrying a charge rho del v. Okay, so for continuous charge distribution we have find electric field in our previous chapter. Okay, so similarly here what we'll do, we have to find the potential due to a continuous charge distribution. Suppose there is a sphere and it is a charge distributed all through its volume. Okay, the charge is continually properly uniformly distributed all over the volume. So we have to find the potential at some point. Okay, so suppose the charge distribution, surface charge density, volume charge density is rho. Okay, what is the meaning of volume charge density? Charge per unit volume, you can say. Okay, at a unit volume has how much charge as a unit volume has. Okay, suppose I have example like one unit, or I'll say 1 millimeter square has suppose 2 microcoulomb charge. So I'll say that the 1 millimeter cube, okay, volume has this much charge. So I'll say that the volume charge density is 2 microcoulomb per millimeter cube. Okay, per volume. Okay, and so what for that, how to find the potential due to the whole charge distribution, whole volume. Okay, so what we're gonna do, we're gonna divide this whole volume into small volumes. Okay, small volume, and for small volume we'll take this volume as small as possible. Okay, we can take it as a point. Okay, what small volume, if we take this very small, we can take treat as a point charge, and for point charge we can find the potential. Okay, we can find the potential. The charge of that small volume will be what? Just multiply the volume of the volume element, that is del v, times the surface volume charge density. You get the charge of the small volume. Okay, so what we have done, we have just find the small volume. Suppose there is a small cube like this. Okay, we find the volume potential due to the small cube. Okay, by treating it as a point charge, we have find the volume potential due to this. Okay, and what we're gonna do, we're gonna integrate it over the whole volume, and we'll get the potential due to the whole sphere or whole volume. Now we have seen in chapter 1 that for a uniformly charged spherical shell, the electric field outside the shell is if the entire charge is concerned at the center. Okay, so when we find the electric field due to a charged shell at a point outside the shell, we see that the electric field was the same as the electric field due to a point charge. Similarly, for a shell, the potential outside the shell is the same as the potential due to a point charge. So we can say that the charge shall behave as if, as for a point outside the shell, the charge shall behave as if the whole charge is concentrated at its center. Okay, this is an important thing you have to remember. The potential due to a charged shell will be at a point outside will be 1 upon 4 pi epsilon naught q by r. Okay, where r is greater than the radius of this shell, where q is the total charge on the shell and r is the radius. The electric field inside the shell is 0. Okay, the electric field inside the shell is 0. Okay, so now this will come in later in the chapter, where how we'll explain that how the conductor has the vacuum, or the what we have also derived it in this, that okay, that electric field was 0 in the previous chapter. This implied that the potential is constant. Okay, so if electric field is 0, that is, from this relation you see, this relation will come in the next paragraph, next to next paragraph. So electric field is 0, that means definitely there is the potential difference is 0. Okay, or there is the potential is constant all throughout the inside of the shell. So that's why the electric field is 0. And so no work is done in moving charge inside the shell, because the potential is same, potential difference is 0. So no work is needed to move the unit positive charge inside the shell. Okay, and the potential is equal for a spherical shell. For different shape and sizes, the potential different. So for a charged shell, the potential inside the shell is 1 upon 4 pi epsilon naught q by r. It is all constant all throughout inside the cell and out at the surface. Okay, outside it will be different. Okay, so I try to explain this paragraph also. If you find any mistake in this, you can try it on the comment section and let others know, so that no one understand get the wrong physics. Okay, and do like and subscribe to this channel. I try to complete the next paragraph in the next video as soon as possible, but don't wait for the video, because I have a very tight schedule. I have a lot of things to do. Okay, so thanks for watching.